Another complicating factor that we've discussed in this course is nonlinearities, and we've discussed them more generally. One approach for dealing with nonlinearities was to generate a linearized model, and the thing that we always need to remember is that that linearized model only provides good accuracy in a small neighborhood around the point that the linearization was performed. A specific type of nonlinearity that we haven't discussed much is something called saturation. And so any amplifier, any actuator cannot supply an infinite control effort or an infinite output. Eventually they will saturate. And one way to deal with this is to do linearization, and I'll discuss that a little bit on the next slide. The other way that we can address nonlinearities more generally is to simulate the system, simulate the effect. This notion of we can't solve a nonlinear differential equation in a closed form way, but we can do a numerical approximation. We can simulate the effect. And so here we have a motor, and let's say we're trying to simulate the effect that our amplifier, our DC supply, is saturating at some level. And so we can simulate it to see the effect. We can sort of understand the effect is that the saturation in essence causes the gain to be reduced. We're commanding 10 volts, but we're only getting 5. It's saturated at 5. And so you can sort of imagine that it's like we've added a gain of 0.5 into our system. The thing is that gain changes nonlinearly. So we could do a linearization. We can, for a certain range of inputs or a certain set of operating conditions, we could use a linear model with this additional gain. But then of course we would have to switch to a different model as the operating point changed. Something that we need to be careful of when we have this sort of saturation is when we have an integrator in our controller. And so an integrator sums the error. It integrates the error over time. And so if we have some amount of error as we integrate, as we run the integrator over a longer amount of time, the control request or the control effort desired builds and builds and builds. We have some error and we're just summing, and it gets larger and larger and larger. But if the actuator is saturated, it will continue to request more and more control effort even if the actuator can't give us any more. And so the problem that arises then is we say that the integrator winds up. So if the error eventually does get driven away and it changes sign, then you've got this large integral that's built up. So a solution is to use an integrator anti-windup strategy. And so at one level we can just turn the integrator off. Once the actuator saturates, we turn the integrator off and we stop asking for more control effort. You can even do something where you reset the integrator. For example, when the error changes sign, you reset the integrator to 0 so that you don't have to subtract off this big integral that you've built up. So now we'll discuss how to design a controller if we don't have a model. In general, in this course we've assumed that we do have a model, and in general we've espoused this sort of model-based approach to design. And we still do. We still recommend that even if it's a very simple model, that you take the time to try and generate one. The time invested is worth it in terms of the intuition and insight that you get about the system. But if you don't have a model, or if the model you have doesn't allow you to apply the techniques that we've learned in this class, there are some other options. So one option is just to use your understanding, your intuition about the effect of proportional control and derivative action and integral action to tune the controller, in particular a PID controller. Another idea is to use some experimentally derived techniques These are sort of heuristic rules for how to pick control gains based on some experimental results. One sort of classically well-known approach is called Ziegler Nichols, but there are others. We'll briefly introduce a Ziegler Nichols approach to tuning. And then a final option is just to use trial and error. You just start trying a bunch of control gains and you just pick the set of gains that provides you the best results. There's software available to help you do this, but it can be time consuming. Okay. So we've discussed some intuition for the different terms of a PID controller. For example, we note that when we increase the proportional controller, here we have that the control effort is equal to the proportional controller times the error. So if you make Kp bigger, the same amount of error will give you a proportionally larger amount of control. And intuitively, having that larger gain means that you push harder for a given amount of error. So you have, error equals 1, you push harder in that direction. You have an error changes to -1, you push harder in the opposite direction. So it makes the system fast, but it tends to make it overshoot more. It also can help with the steady state error. With the derivative control, it allows you to anticipate the error. So it allows you to make the control effort big, because even if E is small, if its derivative is getting large, it's starting to ramp up. You can see that, and you can make the control effort large to sort of respond to that ramping up of the error. And what this tends to do is it tends to add damping to the system. And that can make sense if you think about how a damper or friction or air drag or whatever generates a force that's proportional to velocity. And finally, we can increase the integral gain. And so the idea there is that the control effort builds as the error is integrated over time. And if you make the integral gain larger, then the effect of that integration or that sum is larger. And it's especially helpful for reducing steady state error, but it can be slow to respond and it can make you more oscillatory because the integrator winds up. So you build up this big integral, and even if the error changes sign, the integral is still positive, and so before you can start pushing in the other direction, you sort of have to subtract off all of this area that is built up. And so this intuition can be helpful, and it often is the case that this is the effect of the different gains, but it's not always the case, especially when we have higher order non-canonical systems. And so this can be helpful, but it's not hard and fast. So we can't use these guidelines for all situations. If we truly want to know what the effect of these different gains will be, we really do need a model. Another approach is to use some heuristic rules that have sort of been derived based on experience, based on experimentation. One commonly known approach is called Ziegler Nichols, and there's the first method and there's the second method. So the first method, it looks at the open loop step response of the plant. So we have a plant, we feed it a step, and we look at the output. And if we get this sort of first order or sort of overdamped response, we get a parameter t that captures the speed of response, like the time constant, and we have a parameter L that captures the delay in the system. And based on those two experimentally generated parameters, we can calculate values of a proportional gain in the case of a P controller, the P and the I gains in terms of a PI controller, and the P, I, and D gains in terms of a PID controller. And so this structure is a little bit different than what we're used to. Instead of just having a gain, we have Kp divided by a time constant in essence. And instead of just having a Kd, we have this parameter times Kp, but it's the same notion. Another approach is called Ziegler Nichols' second method. And then instead of using the open loop system, we use the closed loop system. So we build a closed loop system with just a proportional gain, and you increase Kp until it's on the verge of instability. So instead of being a decaying sinusoid, instead of being stable, you increase Kp slowly until it's at the verge of instability. The amplitude is constant. It's no longer decaying, but it hasn't quite reached the point where it grows. And so then you calculate the gains, P for a P controller, a PI or a PID controller, based on the period of this oscillation when it's on the verge of instability and the critical gain, so the value of Kp that puts the system on the verge of instability. These sorts of heuristic approaches, others exist. One application area where they're used a lot is process control, because often there's not a model of the chemical process that they're trying to control. A final approach is to use numerical optimization. So we basically just test the system over the entire space of possible control gains. So for example, you could imagine you just try Kp equal to 1, run an experiment. Then try Kp equals to 2, run an experiment. Kp equal to 3, and so on. Then do the same, add in a D term or add in an I term. And there are sort of smarter ways to do the search than just trying every value, but that's the basic idea. When you do that, you need to somehow define the cost function that you're going to use to evaluate the different sets of control gains. And so we talked about this when we discussed optimality, but what is the best controller? Well, we have to define that. There are also some sort of standard performance indices that exist that have different names. Integral of the absolute error. So we just base our evaluation of which controller is the best based on an integral of the error from time equals 0 to some final time. And so this captures sort of the transient and steady state error in a system. Another example is this one, the integral of time multiplied by the absolute error. And so it's the same as the previous one, except we multiply it by time. And the effect of this is to reduce the influence of the large sort of transient error. For example, if you had a step input with a large error at the beginning, this will sort of discount that because the time will be near 0 at that instant. Other ones exist too. And so you can do this sort of numerical trial and error, this numerical optimization, if you have a physical plant. If you have a model, like a Simulink model, then MATLAB can perform this type of optimization for you also. If you've ever looked at the PID block in the Simulink library, you can see that there's a button to automatically tune the controller. But in that case, you would need a model in the form of a Simulink model. But perhaps that model isn't very useful for controller design. Maybe it's too complicated, but it could still be used for this sort of numerical optimization.